In last lecture, we discussed the general addition rule. Today, we are going to discuss the general multiplication rule. Recall we discussed before the additional multiplication rule for independent event. If we have two events, A and B, if A and B are independent, then the probability for A and B will be equals the probability for event A, then multiply the probability for event B. We already know this from previous lectures. How about if A and B are in general, independent or not? Okay, the formula is for probability for A and B equals the probability of A, same thing here, and multiply by the probability of B on the condition that A occurs. So this is not probability B anymore. It is the probability of B on the condition of event A occurs. Here we have an example. What is the probability of randomly drawing two hearts from a deck of 52 playing cards? We know there are 13 hearts in the pack. We use A to represent the first card drawn is heart. And event B is the event that the second card drawn is heart. And we assume that the first card is not replaced before the second card is drawn. That means you draw the first card, then you throw away, then you draw the second card. We have 13 before the first draw, and we have 13 hearts in the 52 card. So the probability for event A is 13 divided by 52, which is reduced to 1/4. And this is the probability for A. And if the first card is heart, that means on the condition of A occurred, then the probability for B, that means the second card, is also a heart. This probability, because the first card is already a heart, that means we have only 12 hearts left. And the total number of cards is 51, because the first one is drawn. Then the probability for the second card to be a heart is 12 instead of 13. 13 minus 1 equals 12. Then divided by 51. 51 is 52 minus 1. So this is the conditional probability of B on the condition of A. Now, we can use this formula. The probability of two hearts means here A and B. Two hearts means the first card is A is heart, the second card is also heart, so A and B. Then from this formula will be PA and times PB on the condition of A. And we know PA equals a quarter and PB on the condition of A equals 12 over 51. And we do some cancellation, and this result equals 1/17. So these two events are dependent. The reason is the first one here, the probability for the first card is heart is 1/4. That doesn't change. But the second one depends on, so PB depends on the result of A. If A is heart, then this is the probability. If A is a non-heart, then this probability of B will not be equal to this. So this probability is the probability of B on the condition that event A occurred. For example, if these two events are independent means we draw the first card and then we put back before we draw the second card. Then we know PA equals still equals 1/4. Then in this case, if independent, then PB will be equal to, because we put the card back, so we still have 13 heart, and totally we have 52 card. So still equals 1/4. So if the two events are independent, which means we draw the first card, then we put back, then we reshuffle, then we draw the second card, then the probability for we get two heart will be, we are going to use this formula. Right? So PA times PB, which equals 1/4 times 1/4, so equals PA and B will be equal to 1/4 times 1/4 equals 1/16. And that will be not equal to 1/17. Right? So the two events, if this event A and event B are independent, then the probability we draw two hearts will be equals 1/16. If these two are dependent, then the probability will be equal to 1/17. So this is smaller than this one. The general multiplication rule gives us a formula or an idea to determine if two events are independent. Two events A and B that both have positive probability, and that means not equal to 0, right, are independent if probability of B equals the probability of B on the condition of event A occurred. If these two probabilities are equal, then A and B will be independent. How to understand this? So A and B are independent. That means the probability of B will be equal to the probability of B on the condition that A occurred. So A occurred, this one, we don't care A occurred or not. But this one here is the probability of B, but with the condition A occurred. Here is A, yes or no. We don't care. So if these two probabilities are equal, so A yes or A yes or no, if these two are equal, that means A and B are independent. So that is how we determine two events A and B are independent. We just calculate PB to check if this PB equals PB on the condition of A, or PA equals PA on the condition of B. These two are the same thing. If this one is good or this one is good, then A and B will be independent. On opposite, if A and B are independent, then PA and PB will be equal to PA times PB. We know this before, but here, because in general we said PA and B equals PA times PB on the condition of A here. This is the general rule. But if they are independent, that means this one equal to this. So PB on the condition of A will be equal to PB. So just this part will be gone. So we just remove this one. The physical meaning is A and B are independent when they have no influence on each other's occurrence. Now we go back to the example of the playing card. What is the probability of randomly drawing two hearts from the deck of 52 cards if the first card, event A, is replaced and the card reshuffled before the second card? We already know that, right? So these two events will be independent. Then PA equals PB equals 1/4. Then PA and B equals PA times PB equals 1/16. So we can still use this general multiplication rule. So PA equals 1/4, PB equals 1/4, because they are independent. Then PBA is also equals 1/4, because we don't care A occurs or not, because they are independent. So PB equals PBA. So in general multiplication rule, PA and B equals PA times PBA, which equals PB, then equals 1/16. We have homework, ask you to determine if the two events are independent or not. The correct way for you to do this is to calculate the probability. One event is A, the other event is B. You just calculate PA equals PA on the conditional B, or PB equals PB on the conditional A. If these two are equal, then these two events are independent. Otherwise, it's dependent. They are dependent. We already know the conditional probability can be very difficult to calculate. But we have good news. We have a special technique. It's called a probability tree. Probability tree. And we can use this probability tree to simplify the calculation. So probability tree represents all possible outcomes graphically, because it's the tree, and assign conditional probability to a subset of events. Here is an example. This is a tree diagram for chat room habits for 3 adult age groups. The internet users, adult users, and can be classified into 3 age groups, age A1, A2, A3. And the adults, 29% belongs to group A1, and 47% belongs to group A2, and 24% belongs to A3. And this add up together totally equals 100%. Within group A1, there are 47% usually chat. There are other 53%. This one is also equal to 1. So this one here equals 1, this one equals 1 here. Add up together. And this 53% do not chat. And in the second group, A2, and 21% chat and 79 do not. So this one is also equal to 1. And in the third one, these two add up together also equal to 1, and 7% chat and 93% do not chat. What we are looking for is what is the probability for an adult to chat. We are given all these 1, 2, 3, 4, 5, 6, 7, 8, 9 probabilities. If we do not use this probability tree, then this looks like it's ugly. It's not easy to calculate. But if we use this probability tree, then this is much straightforward. So from here, and we know in this group A1, 47% chat, and A1 only 29% of the total. So 29%, this one, times 47%, so that one will be equals 13.63%. And if in this group A1, but do not chat, so this times this give us 15%. That means it is in this one here, but it's do not chat. And the same thing apply to here. In this group, 21%, and multiply give us 9%. And this one here, and together here multiply together, so 24% times 7% equals 0.0168. So we can see we have 3 groups. In this group, we have a total 13%. In this one, we have 9%. In this one, we have 1%. Those are the only adults that chat. So we add these 3 probabilities together, and that gives us the total probability for adult to chat. So the result will be equals 13.63% plus 9.87% plus 1.68%, and which equals 25%. All these numbers, this 13% is this time this equals this time this one equals this time this, and this time this equals this to here, this to here. And those the result is very clear. So we just add this and this and this together, because this is chat, this chat, this chat, these three. These are chatting people in the three groups. So about 25% of all adult internet users visit the chat rooms. So we can see probability tree is very simple. We need to learn how. We need to be able to use draw the probability trees, then can simplify our calculation. Okay, we have another example to show the application of a probability tree. This one is very famous. This one has some like this problem. This example is very meaningful. If a woman in her 20s gets screened for breast cancer and receive a positive test result, positive, that means that is bad. But what is the probability that she does have breast cancer? It gets the screen and says, okay, the result is positive. Then we are going to find out what is the probability that she really has breast cancer. And before we calculate this probability, we need to know some fact. And here are given mammography, and for all this group of women doing this mammography, and the disease incident is 0.0004, just like 0.04%. And 99.99% of this group don't have this breast cancer. Right? So these are the facts. We know this. And for those who have this breast cancer, and the screen will show positive is only 80%. The other 20% it will show negative. That means the screen says no cancer. And we call this is called false negative, because it's supposed a positive, but the screen says a negative, so it's called false negative. And for those who do not have cancer, no cancer, and there are still 10% shows a positive. So this one is not correct too. So this is called false positive. And among this no cancer, only 90% says okay negative. That means that is good. Right? So those are the 80%, 20%, 10%, and 90% are given numbers. Based on these 6 probabilities, right, of all the people between 20 and 30s, there are only 0.0004 have cancer, and the other 99% and 99.96% don't have cancer. And among those who have cancer, and 80% will say positive. That means this is correct. And the other 20% will show negative screen result. That means this is called false negative. And this one is bad. And this one is not accurate. And for the 99.96% of who don't have cancer, then positive, show positive. So this is called false positive, and the other 9% will show negative. And okay, so what we want is we already know the result shows a positive, and we want to know what is the probability that she has cancer. So what we want to know is the probability that she has cancer on the condition that the result shows positive. Okay, that is what we want. The probability she has cancer on the condition that the result shows positive. So this is what we want. This is conditional probability. The conditional probability is from the previous lecture, we know equals PC and P. A on the condition of B equals, let me write the formula. P A B will be equal to P PA on the condition B will be equal to PA and B and divided by PB. This formula is given in the previous slide. So here, event A is cancel and event B is positive. So here on the top, PA and B means PC and P. On the bottom, PB means B here is positive. So we have positive have cancel and positive have no cancel because we have only these two situations. If you have positive, either you have cancel or you have no cancel. So let's see, positive, that's positive, will be equals to P cancel and positive plus P no cancel and positive. So that equals this two. Right? Now PC and P. It will be C and P means cancel and positive. So cancel is here, positive is here, right? So that means this probability. So that will be 0.0004 times 0.8. This one is this, and this one is here. So on the top, we get this result. On the bottom is positive with cancel. So positive with cancel, it will be this one and this, okay? So 0.0004 then times 0.8 so this, and positive no cancel. So positive is here and no cancel is here. So this and this, this and this. Right? So that will be 0.9996 times 0.1. Okay, we plug into these numbers and the result gives us 0.3%. Right? That means even she has a positive result, the probability for her to actually have breast cancer is only 0.3%. Right? So this is very small compared to the scary positive result. And we call this one is called positive predictive value or PV positive. Another important application for conditional probability is Bayes' rule. Bayes' rule is more general, and this one is beyond the scope of our class. Right? So we do not discuss the details of this, but I will list the formula for this. The probability is conditional probability of AI on the condition of C will be equal to this. And I just list here for completeness. We do not use this one, or we do not discuss the technical details for this part. But we are going to discuss some applications of this. The first one is we can apply this Bayes rule to the example we just discussed, the breast cancer example, and we just plug into those in the formula, and we get the same result. So this means Bayes' rule is correct for this example. Another one is, this is very interesting, and we are going to discuss a little bit more. Right? So suppose we have two boxes, A and B, each with 100 balls. In box A, we have 70 red and 30 green. And in box B, we have 30 red and 70 green. So in A, we have more red, 70, and less number of green, so 30. And in B, we have more red than green. Now, question one. I ask you to randomly select one box Now we have only two boxes, A and B. So what is the probability it is box A? Because it's equally likely event, and the total number of event is 2, A and B. So you choose A, so definitely this result equals 50%. There's no big deal for this, everybody can figure out this. Now the interesting part is next question. The next one is, so we put here, so this is 50%. First, you randomly select a box, either A has more red or B has more green. You randomly choose one, we don't know, A or B. And once you select this box, from this box, you randomly pick out a ball, record the color, and put the ball back. Then we repeat this 12 times. So you do, you put back, then you choose another one, record the color, then put it back, then pick another one, then put, record, then put it back. So we do this 12 times. So you have 12 balls. And we found out that we have 8 red, 4 green. All those are given numbers. These are the facts. The question is, what is the probability that the chosen box is A? We know A has more red, and B has more green. And of the 12 balls, we have 8 red, 4 green. So what is the probability that the box you choose is box A? You may guess right now. Maybe from here, if we do not do this experiment, we said 50%. Now we know this, we have this condition. We know 12 balls, 8 are red, 4 are green. So what's the probability? It is still box A. Now you may say, okay, still 50%. Or you may say, okay, now we have 12 balls, then the probability looks like A has more red and the result has more red. So maybe it's more likely that is box A. So maybe we can use 8 divided by the total. Total is 8 plus 4, so that equals 2/3. So that is a little bit larger than half. Little bit larger than half. So it looks like a more reason. So that is only like 0.67%. You may guess, okay, maybe a little bit more, 70%, 80%. Okay? So how about 90%? How about 95%? I know some of you will say, okay, 95%, that is impossible because there's only 8 red, 4 greens. So I don't know. Okay. Now the result from Bayes' rule gave us the result equals 96.7%. It is much more likely the box is A than it is B. The probability for it is B is only 3.3%. So it looks like it's very likely to be box A. So what can we learn from here? And when you first pick up a ball, you may say, okay, the first one may be a red. The second one may be, okay, so the first one may be a red, the second one may be a red. Okay, you say, okay, this is more likely to be a box A. Okay, now that you get a green, so now you get a green. So now you have another red, and now you still, because at the very beginning you think this one is only 50%. But you are more likely change your opinion to a box A. But the question is, you do not want to change your opinion, means more likely to box A that fast. So the lesson we learn is that not only you, almost everybody. So the human beings are reluctant to change opinions. The original opinion is 50%. 50%. But once you get the 12 balls, although you see there are more red than green, so the ratio is 8 to 4 means 2 to 1, a little bit more red than green. But you are going to change your opinion to be more likely to be box A, but usually it's not as large or as quickly as it should be, because it's almost definite it is box A, because almost close to 97%. But usually say, okay, maybe 70%, 80%. Based on my experience, 90% that is the max. And looks like no one will, before you calculate this, no one will guess this one is close to 97%. So we get that human beings are reluctant to change opinions. Is this normal or not? We see another example here. The applications of this is a typical trading emotions. You buy stocks, you sell stocks, okay, you try to invest, okay, speculate, no matter what, you want to earn some money. So those are the typical trading emotions. At this point, the price is at this level, and you see, okay, the price is going up, okay, let's see what the market will go. So you just wait. Okay, now you think like the trend is holding, so you decided I will buy all at the next consolidation. But actually the consolidation is very short, now it's keep going up. Now you said, okay, you regret, I missed the consolidation, so but I will wait. If I wait any longer, I won't profit from the trend. So okay, let's buy. So now at this point, you buy the stock. After you purchase the stock, okay, the price going up. Now you are happy. Say, oh, good thing, I didn't wait. Okay. Unfortunately, after some time, now at this point, it dropped, and you said, okay, this is another good chance. Let me increase my position. So you buy more. Unfortunately, it's dropped again. Now you said, okay, let's double the position. I have more money, right? Buy more. And then keep falling. Now at this point, as soon it is you regret. So, but you decided as soon as it goes up, back up a little, I will sell out. But keep falling at this point, definitely you are feel the pain. But at this point, you decided, okay, I need to get out. I won't stay for long. Okay, now once you get out, this is buy. So this is a sell. You sell here, and it's keep falling, and you say, oh, good thing, I sold everything, so I don't feel the pain. Now it's going up here. But you're still very confident. You said, okay, it will tank again anyway, so I don't regret. Yes, it tanked again. So I told you, this is so good. Now it's going up. You wait. You said, what? Going up? Okay, now what the hell? Okay, even up. So you think the market is crazy. And after some time, you decided, I need to buy again because the trend is confirmed. So you buy at this point. And this is a typical trading emotions. You can see at this point, you should change your opinion, but you won't. At this point, the market is going up. You should change your opinion earlier, but you're reluctant to change until at the last step, you need to change this. And here, it's going down. So at this point, you need to change your opinion. So it's going up, so you need to sell at this point. But you're reluctant to change again. You keep waiting until at this point, you change. Now, same thing apply to this side. You should buy at this point or somewhere, but you still wait, reluctant to change your opinion until this point, you purchase again. So you can see, this is not only you, it's almost everybody. So the majority of the market participant have this kind of emotion. So this is the typical trading emotions. I didn't say anything about how to trade here, but this is a typical ideas.